welcome to the deep dive. Today we're setting our sights on a really fascinating type of star, RR Lyrae variables. It seems like recent discoveries, especially from the Gaia mission, have given us this incredible new view of them.
They really have. It's quite exciting.
Think of them like cosmic heartbeats, maybe? Their pulsing helps us unlock secrets about, well, just how big the Milky Way is, and maybe even what's beyond.
That's a great analogy, actually. Cosmic heartbeats. For a long time, astronomers, we've recognized the potential these pulsating stars have, for mapping out our galaxy's structure, its history.
How does that work exactly? The pulsing.
Well, their brightness changes, right? And it does so very regularly, predictably. So they act like these reliable signals, beacons almost, that let us measure the huge distances across space.
Okay. And where do we find them typically?
You often find them in older places, think globular clusters, and what astronomers call population 2 stars.
Population 2, right.
Basically, the galaxy's senior citizens, older, smaller, less massive than our own sun.
Gotcha. So not your average star then. What is it about these stars that makes them so vital for, understanding the universe? What's the key thing, the aha moment for us listening?
I think the main aha moment is really grasping how we can even start to measure the size of our galaxy. It's vast, right?
It's immense. Seems impossible almost.
Exactly. And RR Lyrae stars are what we call standard candles.
Standard candles. Heard that term before.
Yeah. So imagine you have a light bulb and you know it's a 60-watt bulb. It's intrinsic brightness.
Okay.
If you see how dim it looks from far away, you can calculate how far away it must be.
Right. Makes sense.
Our Lyrae stars work a bit like that. Their pulsation period, how fast they pulse, is linked to their actual brightness, their luminosity. So if we measure their period and see how bright they appear to us, we can figure out their distance. It's really a cornerstone of how we measure cosmic distances.
Okay, a cornerstone. So before Gaia, what did our map based on these stars look like? Must have been pretty sparse.
Sparse is a good word. It was like trying to map an ocean with just a few scattered buoys, maybe.
Yeah.
We knew of several thousand RR Lyrae in the galaxy, but the mission before Gaia, Hipparcos, well, it was amazing for its time, but it only managed to get really precise parallax measurements for about 179 of them.
179 out of thousands. That's tiny.
It is. Parallax is that tiny wobble we see as Earth orbits the sun, right? It's the gold standard for nearby distances. But for most RR Lyrae, it was just too hard to measure accurately back then. Actually, only the star RR Lyrae itself had a really solid parallax measurement.
Wow. Okay, so just a few precise markers in this huge cosmic ocean. That really highlights why Gaia is such a big deal then.
Exactly. It sets the stage perfectly.
So what are these new Gaia discoveries telling us? What's our goal, our mission in this deep dive today?
Our mission really is to unpack how Gaia's super accurate parallaxes, plus its detailed observations of brightness, changes in different colors over time, how all that has just revolutionized the field. And crucially, what are these new findings actually telling us about the Milky Way and the universe?
All right, let's get into it. What makes an RR Lyrae star tick? You mentioned their place on the Hertzsprung-Russell diagram. Remind us, what that diagram show?
Okay, so the Hertzsprung-Russell diagram, or HR diagram, it's basically a map of stars. It plots their luminosity, their actual brightness against their surface temperature, which we see as color.
Right, hot blue stars, cool red stars.
Exactly. And stars don't just stay in one place on this map their whole lives, they evolve. RR Lyrae stars are stars that have evolved off the main sequence. That's the long, stable phase where stars like our sun burn hydrogen in their core.
Okay, so they're past that stage.
Right. They've moved on to what's called the horizontal branch. They're now burning helium in their core, and they still have a shell of hydrogen burning around that core. Typically, they have masses around, say, 0.6 to 0.8 times the mass of our sun.
And you mentioned metallicity affects them. What does that mean for a star? Is that like iron content?
Pretty much. In astronomy, metals means anything heavier than hydrogen and helium. Yeah. Weird, I know.
Okay. Everything else is a metal?
Everything else is a metal. And the amount of these metals a star has, its metallicity, affects its properties. For stars on the horizontal branch, lower metallicity, so fewer heavy elements, tends to make the branch appear bluer. Higher metallicity makes it redder.
Interesting. So their composition affects their position on that stellar map, and then there's this instability strip. Sounds dramatic.
It does sound a bit unstable, doesn't it? It's basically a region on that HR diagram where the physics inside the star makes it naturally pulsate, expand, and contract. And RR Lyrae stars happen to lie right where their evolutionary path, the horizontal branch, crosses this instability strip.
So that's why they pulse. their location.
That's the key physical reason, yes. It causes those characteristic brightness variations, usually with periods of like half a day, maybe up to a day. Less than a day, typically.
Okay. And you compared them earlier to Cephid variables. Are Cephids similar pulsators?
They are. Cepheids are another extremely important type of pulsating variable star. Also standard candles. They're generally much more luminous than RR Lyrae, intrinsically brighter.
So you can see Cephids further away.
Exactly. We use them to measure distances to other galaxies quite far away. RR Lyrae are fainter, but there are more of them, and we can still spot them at significant distances within our own Milky Way. Like towards the galactic center, if we look through clearer areas called Bade's windows where there's less dust.
Right. Now, you mentioned two main subgroups useful for distances, RRab and RRc. What's the difference there?
Good question. It relates to how they pulse and where we find them. RRab stars are usually found in the more spherical parts of the galaxy, the halo, globular clusters, places that are generally metal poor.
The old parts.
The old parts, yeah. Their light curves, the graph of their brightness over time, are asymmetric, like a sawtooth. A fast rise, slower fall. They tend to have longer periods, over 0.4 days, and bigger brightness swings, maybe half a magnitude up to 1.5 magnitudes. They pulsate in the most basic way, the fundamental mode.
Okay, fundamental mode. And RRc.
RRc stars are more associated with the galaxy's older disk component. Their light curves are smoother, more like a sine wave. Shorter periods, under 0.4 days, and smaller amplitudes, smaller brightness changes. They pulsate in a different way, called the first overtone.
Like a higher harmonic.
Exactly like that. And briefly, there are also RR stars.
Yes, you mentioned those. What about them?
They're kind of cool because they pulsate in both modes, the fundamental and the first overtone at the same time.
Double pulsars.
Yeah.
So, we use them as standard candles, but you hinted they're trickier than Cephids sometimes. Why is that?
Well, several reasons. Their intrinsic brightness does depend somewhat on their metallicity, and correcting for that accurately can be complex.
Right, the heavy element content again.
Yes. Also, just being intrinsically fainter means they're harder to see at really large distances. And in crowded fields, like the core of a globular cluster, their light can get mixed up with nearby stars. We call that blending. It makes measurement harder.
So challenges exist.
Yeah.
But still hugely valuable, not just for distances.
Oh, absolutely. They're critical testbeds for our models of how stars evolve and how pulsation works. Plus, because we find them distributed throughout the galaxy, tracing out different structures like the halo and the disk, their motions, their kinematics tell us a lot about how the Milky Way is put together and how it formed.
Okay, so we knew they were important, crucial even, but our view is fuzzy, limited by distance accuracy.
Very much so.
And then Gaia. How did Gaia just blow the doors off this?
Gaia's contribution is, it's hard to overstate. Revolutionary is the right word. Its ability to measure parallax with unbelievable precision down to microarcseconds.
Tiny angles.
Incredibly tiny angles. That, plus its ability to repeatedly measure star brightness in different color filters over years. It's just a game changer for all kinds of variable stars, especially RR Lyrae.
Okay, let's get into the numbers. What did the first data releases show? DR1?
Even Gaia DR1, which was based on early data and focused on specific areas like the Large Magellanic Cloud, where they observed very frequently,
Wow.
even that release identified nearly 2,600 RR Lyrae stars, plus about 600 Cephids. A good start.
DR2, the second release, that was a real avalanche of data, wasn't it?
Oh, yeah. DR2 covered the first 22 months of the mission, and it cataloged, wait for it, 140,784 RR Lyrae stars.
Wow. 140,000. How did they even find them all?
They used a dedicated pipeline, a specific analysis system. It looked for stars showing the characteristic period-amplitude relationship, the period-luminosity relationships of RR Lyrae stars across Gaia's different filters, down to quite faint magnitudes.
And where were these stars found? All over.
It's literally all over. Milky Way disk, the central bulge, the extended halo. Both Magellanic Clouds are satellite galaxies. They found over 1,587 different globular clusters, and over 412 dwarf spheroidal galaxies, including some really, really faint ones.
That's incredible reach. Any specific clusters or galaxies stand out?
Well, just as examples, the globular cluster M3 had 159 RR Lyrae identified, NGC 3201 had 83, and the Sculptor and Draco dwarf galaxies each had 176 RR Lyrae tagged in them. It's remarkable. And out of that big total, over 46,000 were in the Large and Small Magellanic Clouds.
And Gaia didn't just count them, right? It got detailed info.
Absolutely. The quality and number of measurements for each star were so good that they could model the light curves, those brightness variations, in detail for most of them. Over 121,000 had enough data for models with at least two mathematical components, and nearly 68,000 had enough for even more complex three-component models.
That level of detail must be incredibly useful.
It tells you so much more about the physics of the pulsation.
So that huge number, 140,784, how many were actually new discoveries versus stars we already knew about?
Good question. They cross-matched with existing catalogs. About 90,220 were previously known RR Lyrae, but that means over 50,220 to be precise, were brand new discoveries thanks to Gaia DR2.
50,000 new standard candles. That's got to improve our maps significantly.
It provides tremendous statistical power, yeah.
And you mentioned a color magnitude diagram. How did that help visualize this data?
Right, so for the stars where Gaia had good measurements in its blue and red filters, about 83,000 of them, plotting their color against their magnitude, their brightness, it showed beautiful separations. You could clearly see distinct zones for the RRab, RRc, and even the R gas types.
Wow, you could visually sort them.
You could, and you could also see clear clumps of stars belonging to the large and small Magellanic Clouds, and others linked to dwarf galaxies like Draco and Sculptor. Visual confirmation of their homes.
And there's that amazing sky map showing all the known RR Lyrae. What does that tell us?
That map is so revealing. You see the green and black dots? Those are RR Lyrae with Gaia DR2 data. They clearly trace out the parts of the sky Gaia scanned heavily in those first 22 months. But then you see the orange dots.
Yeah, what are those?
Those are RR Lyrae stars we knew about before Gaia, but which weren't in the DR2 catalog yet, likely because Gaia hadn't surveyed that part of the sky as intensely or processed the data fully by then.
Ah, so there's still potentially many more to come.
Oh, definitely. It strongly suggests that future Gaia data releases, covering more sky and going deeper, will uncover tens of thousands more RR Lyrae. The census is far from complete.
Okay, so this flood of data isn't just about counting stars. It's really changing how we use them, how we understand the galaxy.
Precisely. It's not just a bigger catalog, it's a much, much more accurate one, especially in terms of distances from the parallaxes. And that's being used everywhere in galactic astronomy now.
Like how? What kind of research is it enabling?
Well, for starters, people checked how complete the catalog is. Molnar and colleagues used Kepler data, another space telescope, to estimate DR2 was probably about 70 to 78% complete for RR Lyrae in the areas surveyed. That's pretty good.
That is good. So for you listening, it means the maps we're building now are based on a much more representative sample of these crucial stars.
Exactly, and it lets us refine those fundamental tools, like the period-luminosity relationship. Several groups have used the Gaia parallaxes to calibrate those relationships much more precisely, taking metallicity into account better.
Improving our cosmic yardstick.
That's a perfect way to put it. Researchers like Neely, Muraveva, and their teams have basically confirmed how good Gaia's parallaxes are using the RR Lyrae themselves. It builds confidence in the whole system.
And it's not just the yardstick itself, but how we apply it to the whole structure of the Milky Way.
Right. Gould's team showed that RR Lyrae parallaxes from Gaia are so good, they provide a fundamental anchor, a 0 point, for the entire parallax system, almost as good as using distant quasars.
Wow. That's fundamental.
It is. And then combining the distances with proper motions, how stars move across the sky, lets us build 3D maps of galactic structure and motion. Utkin and others used RR Lyrae to study the Milky Way's halo, finding evidence for maybe two components: an inner halo that sort of weakly rotates with the disk, and an outer halo that seems to rotate backwards, retrograde.
Retrograde. Wow, so these old stars are revealing complex movements way out in the halo. Any clues about how the halo formed?
People are definitely looking at that. Yorio and collaborators used the data to check if the halo is tilted relative to the disk. They didn't find strong evidence for that. But then, looking at the motions and distribution, particularly Ario and Belakurov, they argued it strongly supports the idea that a big merger, a collision with another galaxy early on, was really important in building up the halo we see today.
Galactic archaeology, reading the history and the stars' positions and movements.
It's exactly what it is.
And does this reach beyond the halo? Like to globular clusters or dwarf galaxies orbiting us?
Yeah. Yes, absolutely. People like Kundu and Vivas have found RR Lyrae stars way outside the expected boundaries, the tidal radii of globular clusters and ultra-faint dwarf galaxies.
What does that mean? Stars that escaped?
Pretty much. It's strong evidence that these systems are being pulled apart by the Milky Way's gravity. These lost RR Lyrae are tracing out the tidal debris, showing us that process of disruption happening right now.
Incredible. They're like little witnesses to galactic interaction. And what about the RR Lyrae themselves? Are they always alone?
Apparently not always. Corella's group cleverly combined old Hipparcos data with the new Gaia DR2 data. They looked for tiny wobbles in the proper motions of RR Lyrae stars that shouldn't be there,
Wobbles caused by.
caused by the gravitational pull of an unseen companion star orbiting closely. Their analysis suggests at least 7% of RR Lyrae might actually be in binary systems.
Huh. So maybe not always solitary pulsators. And people are using them to trace specific structures too, like streams of stars.
Definitely. The Sagittarius stream, that's the remnant of a dwarf galaxy being torn apart by the Milky Way Ramos and colleagues, found thousands of RR Lyrae candidates that seemed to belong to it.
Mapping out the debris trail.
Exactly. Others, like Prudel's team, looked closer to home, in the solar neighborhood, separating RR Lyrae that belonged to the disk from those thought to be part of another ancient merger remnant called Gaia Enceladus. And Du's group focused on RR Lyrae in the galaxy's central bulge, using their motions and distribution to probe that really complex, dense region.
It's just the breadth of research unlocked by this one type of star, thanks to Gaia, is staggering.
It really is. It's touched almost every area of galactic structure and evolution. The precision Gaia brought is the key.
So it's clear Gaia's RR Lyrae data has, as you said, revolutionized our view.
No question about it. Better distances, better understanding of structure, formation history. It's a whole new ballgame.
And the exciting part is, this isn't the end of the story, is it? DR2 was huge, but there's more Gaia data coming.
That's right. Future Gaia data releases promise even more RR Lyrae, even better accuracy in parallaxes and proper motions, maybe radial velocities too for many. The detailed studies we're seeing now are just the beginning. We're still riding this wave.
It's an ongoing revolution.
Absolutely.
So as we wrap up this deep dive, it really is amazing to think about these faint pulsing stars, how crucial they are for piecing together the story of our own galaxy. Maybe think about this. Having the power now to precisely map where these ancient stars are and how they're moving lets us reconstruct the Milky Way's dynamic past. We can see the echoes of old collisions, ancient mergers. It just highlights that the universe, even our own galaxy, isn't static. It's constantly changing, constantly evolving, something to really ponder. Thanks for joining us on the Deep Dive.